We're looking at vector resolutes next. So a vector resolute is a way to decompose a vector, let's say the vector A, relative to another vector B, into two components. The first one being the component of A which is parallel to the other vector B, and the other one being a component that's perpendicular to B. Now it's sometimes called a projection as well. So the idea is to think about, I guess, imagine like a sun above A. If A was to cast a shadow, the shadow that it would cast would run along this vector B here, and that vector there is U. We call U the vector resolute, so it's the horizontal component of A in the direction of B. So that's what I've written there so you can see. So that's the horizontal vector resolute of A in the direction of B. Okay. If you think about the other way too, we've also got this vertical component here as well, which is W. Okay, and that's perpendicular to B. So two components to make up the vector A, the horizontal component U plus the vertical component B. So I'm just going to get rid of these on the diagram, and then we can work our way through. So the idea that we're going to find today is how to get U and W when you have a setup like this. The other thing too is talking about something called a scalar resolute. Now we're going to find vector resolutes. Vector resolutes have an I, j and a k, they're vectors. There's also something called the scalar resolute, and that's given by this formula here, which is an important one. So that formula there is A dot B hat, where B hat is a unit vector in the direction of B. So you're basically, again, decomposing A into going into this direction, into the B direction. Okay, this is the alternative here as well, and the reason that that comes about is if you had A dot, actually I'll do this underneath, if you had A dot B hat is actually given by B divided by the magnitude of B. So if you have A dot B hat, you actually have A dot B over the magnitude of B, like that, which is what this is here. Okay. So they're the two different forms for what we call the scalar resolute. So that's not something you see as commonly as the vector resolute, but this is what we're going to find. So the first thing that we think about, I'm going to pretty much base everything around this formula here. Okay, I'm going to re-express this now. So looking at, first of all, U. You can see that U is parallel to B. So we can write that in a particular form, and that's where U equals K times B, or B equals K times U. It doesn't really matter, they're the same thing. Okay, so what I'm going to do here is I'm going to use this idea here that U is parallel to B. I'm going to put this into the formula here. So A equals KB plus W. I'm now going to re-express this in terms of W. So W equals A minus KB. And I should also say here that K is some scalar, it's some real number. So we now have W. Now the thing that you'll notice in the diagram here is that W and B are perpendicular. So W is perpendicular to B, which implies that when we think about perpendicular vectors, what do you think about first? You think dot product. And the dot product for two perpendicular vectors has to be 0. So what we can do now is we can actually find, we've got what W is, A minus KB. Okay, we're going to dot product that with B. Okay, and that's going to be equal to 0. So dot product, remember that the way that the dot product works is that it expands over a bracket. So we can do that. So we've got A dot B minus K B dot B equals 0. And we can actually solve this expression now for K, because K is the thing that we don't know. Therefore, we've got K equals A dot B over B dot B, and actually those should be vectors too. That's what we find K to be. Okay, so what that means then, in terms of our setup here, is that we've actually found what W and U are, and in particular here U, because we can now substitute K in. So therefore, that U, which is what we call the vector resolute of A in the direction of B, this component here, the horizontal component, is given by K times B. And because we know what K is, this is K. A dot B over the magnitude of B, can be the magnitude of B squared, but I'll actually write it the way that I've got it there. makes you to B dot, B dot, B dot, and we've got the B here as well. So what you'll notice about the form of that rule, I'll just draw a square around it, is that if you're looking for a vector in the direction of B, this vector here turns up here in the formula, and the direction that you're looking at, this vector also turns up down here as well. Okay, so if you have two vectors, A and B, and you want the vector resolute of A in the direction of B, it would be this formula here. If you wanted the vector resolute of B in the direction of A, it would be opposite. So B in the direction of A, and I should write here so that we have it. So this is U, which is resolute of A in the direction of B. Oops. Let's look on the next screen. If I wanted the vector to be a vector U, which is B in the direction of A, so opposite to what we had, it's going to be just the same form. You'd have a dot product on the top, so it would be the dot product, and this time instead of being B dot B, it would be A dot A, and then A here. So whichever one is the in direction of part, that's the part that goes here and also as the dot product on the bottom. Okay, so that's the way that we can find this U, the vector resolute. And if we wanted to actually put together our formula now, and I'll do this on the other side here, this is what we found U to be. Now W, if we look back here again, W is a vector going from here to here. We could go backwards along U and then up along A. So knowing what U is, W is actually negative U plus A. So it can be written in this way. So again, you can actually express W using the A minus U, and that's U. Remember that that's KB. So to finish off here, for our full vector, so our vector A, and actually I'll just get rid of this here. So the vector A can be decomposed into two components. And remember that we had this look. I'm just going to roughly draw again. There's B, there's A, there's U, oops, there's W. We've got A equals U plus W. U, remember, was A dot B on B dot B, B. So we've got A dot B over B dot B times B. So that's the U component. And the W component, remember that from this diagram, W equals negative U plus A. This is what U is, so we could also write that as A minus U. So then we've also got plus A minus U, all of that is U. It's quite a big formula there. Okay, and that's our what we call decomposed form of A. So one of the parts here being the parallel part, and this part here being the perpendicular part. Okay, so those two parts together would give us A. So that's a final form that's really important for a vector. If we want to divide a vector down into the two parts that are parallel and perpendicular to another vector, then this is the vector form here. Okay, so the key thing to take away from this section is how to decompose a vector into the parallel and perpendicular parts, and what the formulas are for your parallel and perpendicular parts. The vector resolute of A in the direction of B, and the vector resolute perpendicular to B in W.